welcome to the Student Research Forum session, and all the best to all the participants. And we have 6 to 7 papers which will be presented today. And the response what we got for our presentations was overwhelming, and it took around multiple sessions for us to reach out to this shortlisted papers which have to be presented over here. And we will be announcing the winner and the runner-up at the end of the program once all the presentations are done. Team which will be coming to present their paper is about Boolean expression based DC balanced partition block 8B by 10B line encoder. The authors are Ritu Verma, Gayatri Janvi, Trinad Sai, and Tanush. Okay, I request all of them to come onto the stage once. Let's give a round of applause to them. Okay, you will be given 20 minutes to present your paper. So 2 of you can present the paper.
Good afternoon to all the esteemed dignitaries and the distinguished people present here. So I'm okay. Thank you. So I'm Sai Manohar Pragada from Gayatri Vidya Parishad College of Engineering, Autonomous, which is located in Visakhapatnam, Andhra Pradesh. So I'm pursuing my BTech final year in the Department of Electronics and Communication Engineering, and as a hobby project, we started this, and today we are here to present this paper.
Good afternoon all, and I'm Gayatri Jahnavi. I'm from Gayatri Vidya Parishad College of Engineering. Currently I'm pursuing BTech final year.
I hope everyone are well aware of this, at least some are well aware of this particular line encoding technique, which is used for high-speed serial data transmission in applications like server net, Ethernet, fiber optics. So this particular 8B to 10B line encoding technique is a technique which was firstly published by IBM in the year 1983. This technique was proposed by IBM. So the basic motto of this technique is like if 8-bit is to be transmitted serially in any medium, if the raw 8-bit is to be transmitted, then there are like 2 power 8 combinations of 8 bits. In this 2 power 8 combinations, there are many combinations where the run length exceeds 5 and 6 and 7 also, right? The run length is nothing but the contiguous ones and zeros. So this continuous ones and zeros have its significant disadvantages in a high-speed data transmission, in a long-range transmission too. So there have to be some technique to reduce this run length and to improvise the number of transition in a particular serial data. So that technique is proposed by IBM. This is the way how it's gonna be like 8 bits is being encoded to 10 bits. First, the 8 bits will be divided into 5 bits and 3 bits in a data bits. There will be a deserializer from the input side, and the serial data will be converted to parallel, and it will be transmitted to the data bus, and 5 bits and 3 bits will be disintegrated in that way. And 5 is encoded to 6 and 3 is encoded to 4. So mark my word, the point encoded. This encoding technique is completely, the novelty belongs to IBM, and our work is like to implement this technique. We have developed a mechanism with a complete motto where we wanted to eliminate all the LUTs, and we wanted to eliminate all the memory elements which are required inside it. That occupies more space, it increases latency. So that's why we decided to implement the whole circuit, handloom the whole circuit in the gate level modeling. So we used, so here you can see 6 bits and 4 bits, right? The encoded bits, you can see the 6 bits and 4 bits. And these 6 bits and 4 bits are 10 Boolean equations. Okay, so 10 Boolean equations which we obtained from the K-maps, solving the truth table, and these Boolean equations produce the outputs, and the outputs are managed in such a way that when the 6 bits and 4 bits are integrated to 10 bits, then the run length doesn't exceed 4. The continuous ones and zeros doesn't exceed 4. So this is how we implemented our topology, and you will be seeing it further. So this is a problem statement where the technique is implemented by implemented in many papers using lookup tables. Like they have written the code in Verilog in a behavioral model, and finally synthesizing it results in a synthesis that involves lookup tables and memory elements. So in the memory elements, the memory elements are mainly used as a feedback circuit, where here I want prior to this I want to explain something. This is a truth table. Here you can find this is a 5-bit to 6-bit truth table, and that is a 3-bit to 4-bit truth table. You can find the divisions like RD plus 1 and RD minus 1. It's nothing but a running disparity, and I'll explain you what. So basically, in a particular 6-bit code word, if you want to have the maximum number of 1 and 0 transition, we need number of ones and number of zeros to be very near to itself. Like here you can find three categories of code words where number of ones and number of zeros in a particular 6-bit are equal to 3 and 3, 4 and 2. Okay, there are three types of disparities, that is +2, -2, and 0. And these are what you can say. If we go further, like we can also go further, like the number of ones and number of zeros to 4, but that increases the continuity. So it is sufficient up to +2, -2, and 0. So there are 5-bit have to be encoded to 6-bit. So 5 bits have 32 combinations, and we need to select certain combinations from the 64. 6-bit is 64. Certain combinations of 64 from the 64 bits, and we need to map it to the 5 bits. And the combinations are selected by the one who proposed the technique in such a way that after the integration, that would lead to the minimum run length. And here you can find RD plus 1 and RD minus 1. And the category of bits that belongs to RD plus 1 having dominant ones, and the category of thing that belongs to RD minus 1 has dominant zeros. And this category, which is undivided, has equal number of ones and equal number of zeros. So it's like, if suppose we want to find the total number of combinations in the 64 bits that has equal number of ones and equal number of zeros is 3 ones and 3 zeros. That is nothing but 6 factorial by 3 factorial into 3 factorial. It's almost 20 combinations. So 20 combinations are done with the equal number of ones and equal number of zeros, and still we have 12 combinations to be mapped with the overall 32 bits from overall 32 5-bit combinations. So those are taken from like dominant ones 4, and like in the case of dominant ones, the number of ones to be 4 and number of zeros to be 2, and 4 minus 2 plus 2. So the plus 2 is one of the disparity, and number of zeros 4 and number of ones 2 is number of ones minus number of zeros is -2 there, and it is one certain disparity. So these particular combinations are mapped to the remaining 12. So in that way, this is made up. And what we need to do is, when certain input 5-bit comes, like let's say 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, and 1, 0, 0. So this is the input 8-bit sequence. Then what we need to do is, this has only one option, and we need to select. So we need to, let us say this. So we need to select certain combination of this or this that finally results in minimum run length. That the device must auto-select a certain combination of the two, such that when the 6 bits and 4 bits are finally integrated, the run length is as per the specification mentioned. So for that, this was our design. So this is our main design. I think it's not visible. Okay. So what we have done is, here, I'm not sure it's visible, but here these are the 5-bit input, and this is an decoder. Here I want to mention, like, we are converting 5 bits to 6 bits. Okay, so when we want to map something from 5 bits to 6 bits, we need to use a decoder, and we use a decoder, and we use a checkbox. A checkbox is like to check whether it is from +1 or -1. Okay, so I'll come into the point. This checkbox checks whether this is from +1. This is from +1 or 0 disparity. This 0 disparity is common for both. Okay, like for taking out the 6 plus outputs, this particular decoder has 6 outputs. So each and every output is one Boolean equation, and for that we need a K-map, right? For that K-map, what we have done is we have taken all these 6. Like all this left column data bits along with this 0 disparity data bits. Okay? And for the 6 minus, we have taken all this right column data bits along with 0 disparity data bits. So in that way, we got 2 encoders, that is 6 plus and 6 minus. Okay? From in this, the outputs of this 6 plus encoder consists of the data bits which is left side of this particular portion, and also the 0 disparity. So there is a necessity of the checkbox to ensure that whether this particular output which is obtained belongs to the non-zero disparity or 0 disparity. Okay. So in the similar way, we have a 4 plus and 4 minus 2. This checkboxes checks whether the particular bit is belonging to the non-zero disparity is nothing but which is divided into two halves. 0 disparity is which is undivided. So here the concept is, when we have a 6-bit output, here we got a 6-bit output, it is checked and it is like from non-zero disparity. Now what happens? This checkbox tells that it is from non-zero disparity, and the output checkbox is like 6:1 encoder. 6:1 encoder. Okay. So this to tell that it is a non-zero disparity or a 0 disparity, the checkbox gives 1 or 0 as an output. So when this is enabled, this is disabled. So this signal will be 0, and for this OR gate, we will be getting one enabled signal. So through that one enabled signal, that will be going as a feedback to the 4-bit encoder. So why do we need a feedback? For example, take this 1001111. Okay, 1001111, and we got another bit. We got 3 bits like 011. Now the 011 can be encoded as 1101 or 0010. So now, what must the device choose? We got 6 bits, right? We need to get 10 bits. So what must the device choose? 1101, 0010. So that is the problem it has to identify. So when we give the feedback that it is from positive disparity, then it definitely chooses 0010. So when it chooses 0010, what is happening here? Here it is 3 ones at the end. Okay. So when it chooses 0010, it is 1001111 So there is no so the continuity of ones is eliminated by choosing 0010. If it chooses 1101, the continuity of ones extends to 5. So the run length extends to 5. So that is the problem. That is the problem to be solved, and this solves in that way. So how does this solve? So the table is designed in such a way that the table tells us that, hey device, when something is from RD +1, then you choose the other from RD -1. If something is from RD -1, then you choose the other from RD +1. So in this way, you alternate the transitions. Okay, and make the run length minimum as possible. So that is how it is, and this particular spec also have the special characters, where in the same protocol you can send the data as well as the special characters. This particular technique has 35 special characters, and these 35 special characters are being sent in the same data stream. There is no other special circuit to transmit the special characters, because here there is a very similar correlation between the special character bits are called k bits. Okay, so there is a very common similarities between the data bits and k bits. So k bits are being drawn from the outputs itself from here, and they are being designed in this way. And the DC balancing is also carried out in the k bits. And to make the receiver recognize that this particular thing is a data bit or k bit, we will be sending another bit called k bit. If the k is 1, then the receiver understands that this is a data bit, this is a special character. If k is 0, then the receiver understands that this is a data bit. Okay. So that is how the design is all about, and the results will be explained by my.
So I'll fastly wrap up it. So coming to the results, first these are the encoded outputs we got is. It is obtained through the EDA Playground, which is the open source web application through which we can simulate the HDL codes. So these are the encoded outputs. And before that, this is the schematic capture of 8-bit to 10-bit line encoder. It is obtained using the Cadence genus tool. So basically in this one, green signifies the connectivity between the gates and red signifies the gates. So basically synthesis is nothing but transforming the RTL into the gate level netlist. So we use the Cadence genus tool for it, and the input files are SDC files, that is the synopsis design constraint files. And yeah, coming to the timing report. In this timing report, the first important parameter that we need to know is slack time. So slack time for any design, if the design need to work in a proper condition at a desired frequency, the slack time need to be positive. So in our circuit, we got the slack time as 246 picoseconds, which is a positive value. So our circuit is compatible for the working at a desired frequency of operation. And second thing, coming to the propagation delay. So this is our main circuit. In this methodology, we can observe that first starting with this one, first starting with the decoder and then giving to the checkbox, and then again outputs, like there is a one repetition of the clock cycle to get the data bit. If we encode the 8 bits to the 10 bits, so there is one repetition cycle such that it starts from here and ended after the one clock pulse given by the D flip-flop. So in this one, the maximum propagation delay can be obtained as 1651 picoseconds, which is the maximum arrival time for this 8-bit to 10-bit data conversion. So this is the 1651 picoseconds, and we have taken it as the maximum propagation delay. So further one, to obtain the frequency of operation, we need to do the inverse of it, like 1 by 1651 picoseconds, which obtain the frequency of operation as 605.6 megahertz. So basically, we have done the comparison between the IBM paper and our model design. So in this one, PTA parameters. So first one, frequency of operation for the timing analysis. So frequency of operation, our frequency is 605.6 megahertz and IBM was 273, which is more compatible. I mean, we have the, we can do our design model at the given maximum frequency of 605.6 megahertz. And coming to the area, our design consumes 1259 micrometer square and IBM consumes 1847. So area-wise also we are very compatible. I mean, we are more efficient in terms of area also. And in PTA parameters, last one is power consumption. For the power consumption, our work requires 1.41 millivolts as a power consumption factor. And for the IBM paper, it is 3.83 milliwatts. So basically, our conclusion in terms of PTA parameters, in power-wise, time-wise, and area-wise, ours is more compatible compared to that of the reference paper, IBM paper. So I won't extend it much. And for the clocking and timing efficiency, ours is twice faster than the conventional 8-bit, 10-bit line encoder, that is IBM paper. And in terms of the power, ours is 1.41 milliwatts, as I mentioned here. So it is 63.1% efficient than that of the IBM paper. And third one is the area. Of course, I have mentioned 1259 micrometer square. So in this area wise also, we are 31.8% more efficient than that of the conventional 8-bit to 10-bit line encoder. So these are the PTA parameters comparison with the reference paper, IBM paper. And this is just a power and area analysis. And main problem statement was solved here. So basically, these are the tri-state sequential in the sense only one D flip-flop is utilized in our circuit. And then these are the just logic gates, AND gate, OR gate, these are all. So basically, here area compensation by the various cells is that 98.7% area compensation by combinational circuits and 1.2% by sequential circuit. So basically, we have removed the necessity of the memory element in our circuit, which is the solution of our problem statement. And yeah, conclusions.
I want to conclude this, like we want to look forward using this topology. We want to take this to different applications like server net, Ethernet, and all using this topology. And also our future scope is to take this topology to 64 to 66-bit line encoder. So that's how I conclude. Thank you so much.
Thank you.
Thank you. Thanks, Gayatri and team. Thank you. I hope we understood that. Let's give them a round of applause for their hard work. Now, we will be inviting team to explain us about modeling of antipode attack with bufferless NOC by hardware Trojan. Authors are Joshna, Rose, Neetu, and Rekha.
Good afternoon, everyone. I am Rose. I'm a PhD scholar from Cochin University of Science and Technology, and I'm here to present our work titled Modeling of Antipode Attack in Bufferless NOC by Hardware Trojan. So this is the agenda of today's presentation. So as we all know, with advancements in IC technology, there has been a tremendous increase in transistor integration due to plunge in transistor feature sizes to ultra-deep sub-micron levels. So this has led to the development of complex system-on-chip, popularly known as SoC, which has a number of processing cores in a single chip. So NOC, that is network on chip, is the preferred interconnection framework in tile chip multi-core processors because it can overcome the scalability and bottleneck issues faced by the traditional point-to-point and bus-based interconnection frameworks. So this is basically the NOC architecture. It has a number of processing cores interconnected by routers. So NOC basically consists of routers, bidirectional links, and NI. So the processing cores are connected to the routers through a network interface or NI, and the communication between the routers happens through the bidirectional links. So the preferred, the most commonly accepted topology is mesh topology, where the routers are interconnected to the neighboring routers in 4 cardinal directions and to the local processing core, and the injection happens to the local processing core through the local port. So this is the conventional 5-port router architecture. It's a buffer router architecture, as you can see. The flits, the basic unit of data transmission NOC is packets, and due to the bandwidth limitation, the packet is again subdivided into flits, that is flow control digits. So flit is the basic unit of data transmission, and the flits, when the neighboring routers first go into the buffers and reside the buffers, and it is transferred to the output port through a crossbar, and this port selection is happening through a control logic, which consists of routing logic, then the VC allocator, and the switch allocator. So these are the design goals in any NOC network. So the NOC should have high throughput, low latency, low complexity, low cost, and less energy consumption. As there are buffers in the NOC, in buffer router architecture, these buffers consume more area and power. So researchers have come up with bufferless NOC design, and chipper is a popular bufferless deflection router architecture. So chipper has a two-stage pipeline router architecture, and the chipper also follows a bufferless approach where there are no buffers, so the flits are always in transmit, and since there are no buffers, the flits can't wait in routers, and the contention is handled by either by dropping or retransmitting the packet or deflecting to a free output port. So if there is a contention, it will be deflected to the neighboring router, and the other one will be getting the preferred required output port. So chipper is a bufferless deflection router architecture. It consists of two-stage pipeline router, and in the first stage, it has ejection followed by injection unit. So the flits that are destined to the local processing core will be deflected to the local processing core to the ejection port. And whenever there are free indirect flit channels, there can be flit injection from the local processing core. And the next, in the stage 2, we have got a PDN network. PDN stands for Permutation Deflection Network. And there we have got 2x2 arbiter network for parallel port allocation. So we are trying to model a hardware Trojan in bufferless NOC. So we know that hardware Trojan is any malicious circuit in an IC which can alter the normal system behavior. So in the normal system, if you have got an input, we'll be getting the correct output. But if there is that Trojan inserted, then when the Trojan is triggered, we'll be getting an altered output. So this Trojan can occur in any phase of the system design. So it's because there's long and globally distributed supply chain of hardware IPs that makes the SoC vulnerable to increasing diverse trust and integrity issues. So these threats in SoC design can occur in any phase of the design, like in specification phase or design integration phase due to the designer mistakes or rogue employees, or in synthesize stage due to the EDA tool vulnerabilities or due to the untrusted vendors, and even in the fabrication stage due to the untrusted foundry. So what we have done is we have tried to model a hardware Trojan in bufferless NOC and see the impact of that hardware Trojan that can make the network performance. So this is an 8x8, part of an 8x8 network, and we have modeled a Trojan in router number 28 and see the effect of the Trojan in the network. So we have modeled the Trojan in the second stage, that's in the PDN stage of the network, such that when the Trojan is triggered, it will alter the required port direction of the flit. So the flit that was, suppose the flit that is destined to a north port, it will be deflected exactly opposite to the required port direction, that is to the south. So suppose I got a flit which has got source addresses 27 and destination addresses 36. Now suppose if there is a Trojan at router number 28, and since the desired path is to 36, that is, it has to go to the south port, but due to the effect of the Trojan, it will be deflected and it will go to exactly opposite direction, that is to the north direction. That is, due to the action of the Trojan, the flit will be moved to the router number 20 and will have an altered direction. So this is the methodology that we have adopted. We have used BookSim, that's a network simulator, and we have performed both simulations using the synthetic traffic and the real traffic. So we have used Spec CPU 2006 benchmark applications, and we have produced network traces using the Gem5 simulator. So this is the Gem5 configuration that we have used. This is the benchmark programs that we have used to create the trace file. And we have mixed the benchmark programs to get various benchmark intensity mixes. And we have fed it into the BookSim network simulator to get the network statistics. And we have used Orion tool to get to estimate the dynamic power dissipation across the inter-router links in 8x8 mesh NOC. And we have used hotspot tool to estimate the temperature distribution across the NOC network. And we have performed the hardware analysis using the EDA tool. That is, we have used Xilinx Vivaro to estimate router area, timing, and power. So these are the results that we have obtained. So we have compared the design with hardware Trojan and without hardware Trojan in terms of network parameters like latency, deflection rate, throughput, etc. So this is the graph that shows the latency comparison for the different synthetic traffic patterns. So as you can see, with the effect of hardware Trojan, when the hardware Trojan is triggered, the network saturates earlier and the latency also increases. So this is the latency comparison for real workloads. Again, as expected, for the hardware Trojan affected network, the latency decreases. So these are the results for deflection rate comparison. So as you can see, when there is hardware Trojan, then the deflection rate also rises because the path of the flit that is affected by Trojan is altered. So because of that, there will be more number of deflections. So this is the deflection comparison for the real workloads. Then this is the throughput comparison for the various synthetic traffic patterns. Again, due to increase in deflection rate due to the hardware Trojan, the throughput also decreases. This is the variation in HT attack probabilities. So as you can see from the graph, when the attack probability is increased, the performance also of the network also decreases. So that is when the for example, for when the HT is for 0.05 probability, the latency is increasing. Again, compared to when the HT is with probability 0.3, that performance is much more less compared to the one with HT as 0.05. Again, for deflection rate, again, the network performance decreases when the HT has more probability. So this is the router link utilization comparison for the synthetic traffic patterns. So with the HT, there will be more deflections and the traffic is non-uniformly distributed due to the HT. So this is a thermal analysis. So across the central routers, when the HT is triggered, we have triggered the HT in such a way the HT is in one of the central routers. So because of that, there will be more deflection across the central routers. So when HT is triggered, when we analyze the temperature, we found that there is some 4 Kelvin rise because of the increased deflections and the traffic. We also performed the hardware analysis with HT, and we found that due to the hardware Trojan, there is 1.6 area overhead and almost 1% static power overhead. And coming to the timing latency, with HT and both without HT, the first stage is having the same hardware. So the stage 1 is determining the critical path. So and with stage 2 only we are adding the HT. So the critical path remains the same because the stage 1 is determining the critical path latency. So to conclude, we have modeled and implemented and analyzed the effect of hardware Trojan in bufferless NOCs. And we analyze the impact of the hardware Trojan in various network level parameters such as average latency, deflection rate, throughput, and area overhead. Then as deflection routing is employed here, the HT detection is not as easy as in buffered NOC architectures. So our future work include coming up with a cost-effective HT mitigation mechanism to detect the HT. And thank you.
Now, I would like to call up Shravani Gadgil and, Sharvani Gadgil and Chetan for design and implementation of CNFAT-based ternary logic processor.
Yeah, good afternoon, everybody. My name is Sharvani Gadgil. I am a PhD scholar at BITS Pilani Hyderabad campus. So I am very happy to be here. I was a part of the VLSI Design Conference back in 2020 in Bangalore also. There I had a paper to present. So firstly, I would like to thank everyone here, the organizing committee, to give me an opportunity to speak for the Student Research Forum. So today I'll be talking about my research work titled towards the design and implementation of a CNTFET-based ternary logic processor. Motivation as to why ternary logic, why multi-valued logic, why CNTFETs and all that. Then I would talk about the background. I'll talk a little bit about what are CNTFETs, why, what is ternary logic all about. Then I'll talk something about the proposed designs that we have proposed in various papers. So firstly, to start with, I'll talk about a proposed ternary arithmetic logic unit that we have designed. Secondly, we'll talk about the proposed ternary sequential logic circuits that we have designed. And finally, I'll talk about the probable implementation of a possible ternary logic processor using the CNT FETs. So then comes the results, and then the conclusion, and of course the references. So the motivation. So there has been an ever-increasing demand for high performance in low-power digital systems, and also we have been seeing that everywhere it's being discussed about, the scaling issues that the CMOS is facing lately. So, researchers are trying to come up with the different post-CMOS technologies these days. So some of the post-CMOS technologies that we are looking into right now is something like FINT FETs, and there are quantum dots, then there are CNT FETs. Also, we are also looking at some of the computing paradigms that are coming up. So the different computing paradigms beyond the binary kind of computation. Like the traditional computation is the binary computation, which consists of zeros and ones basically. So beyond that also, if we can go to some kind of computing paradigms which will help us improve the performance, it would be a very good thing. So like the post-binary things that are the researchers are these days looking into is quantum computing and then multi-valued logic computing. So what I can say is the current status is the CMOS-based binary logic implementations. So for digital logic circuits design, the current scenario is CMOS-based binary logic. So what we are trying to do is, we are trying to see if we can use CNT FET-based multi-valued logic, which can be a probable future thing. So in that direction, the motivation of the work comes about. So now a little bit about the background. So the ternary logic, basically as the name suggests, ternary is like 3 levels. Like binary is 2 levels, ternary is 3 levels, directly from the name we get. So it's like this, like if you look at the truth table there, a 0 is represented by 0 volts, a VDD by a 2 volts, a 2 is represented by VDD, and a 1 by a VDD by 2. So that is how we define the 3 logic levels. Then if we go to the basic OR and AND gates, if say suppose Xi and Xj are 2 ternary numbers, so the ternary numbers, the OR function will be defined by the maximum of the 2 numbers. Similarly, the AND function will be defined as the minimum of the 2 numbers. So then like in binary, the basic inverter is like if you give a 0, it gives a 1. If you give a 1, it gives a 0. But then here in the ternary, we have in the sense, in general for ternary logic implementations, they have defined 3 different types of inverters called as STI, NTI, and PTI. So STI is a standard ternary inverter. So the truth table, from the truth table you can see, like for a 0, 1, 2 input, you get a STI, standard ternary output as a 2, 1, and 0. And a negative ternary inverter will give a 2, 0, 0, and a positive ternary inverter will give a 2, 2, 0. So that is how these 3 basic ternary inverters are defined, which we will be using in design of, say, bigger circuits. So now, in order to further continue with the background, we'll talk about CNT FETs. So CNT FETs basically are carbon nanotube FETs. So the basic traditional thing, the MOSFET has, the channel is made up of a semiconductor basically, either a P-type or N-type semiconductor. But in case of a carbon nanotube field effect transistor, it will be consisting of carbon nanotubes, which will serve as the channel between the source and the drain. So this is how it looks like. So basically carbon nanotube is made up by rolling a sheet of graphite. So you can see this is an unrolled sheet of graphite which is rolled along a particular vector. So the vector along which it is rolled about is say given by C equal to NA bar plus MB bar. So where N and M are integer values which have got quite a relevance. So N and M are called as the chirality property of the CNT. So this chirality property is something that is important in order to design the circuits and all that. So A bar and B bar are unit lattice vectors, as we can see there. So C bar is the vector along which this sheet is rolled in order to get that particular carbon nanotube. Now, once the carbon nanotube is made, there are different types of carbon nanotubes. I'll call it CNT from now on because it's like a long name. So, CNTs are of different types. So, there will be armchair, chiral, zigzag. So, for armchair, they are always metallic kind of CNTs, and they are made by making N is equal to M. When N is equal to M, they are armchair kind of CNTs, and they're chiral and zigzag when they are they can be either metallic, that means they can be behaving like conductors, or they can be behaving like semiconductors. So when they will be behaving like conductors, there is a criteria. So the criteria is they will be behaving like a metallic thing if N is equal to M, and if N minus M is 3i, where I is an integer. And if not so, if these criteria are not satisfied, then it is a semiconducting thing. So that is the semiconducting CNT is what we used to build our CNT FET. So this is how the CNT FET will look like in the second diagram below. So the CNT FET will basically have the gate as the CNTs. In this particular CNT FET in the diagram, you see there are 3 carbon nanotubes. Okay, so there's a very important property of the carbon nanotube FET that will make it viable to use for ternary logic implementations. So that particular property is you can change the threshold voltage of the CNT by changing the diameter of the carbon nanotube. So you can see from the equation, first equation here, that VTH is the threshold voltage. The threshold voltage is inversely proportional to the diameter of the CNT. So the diameter, and also the diameter is dependent on the NM values, which are the chirality values from the second equation. So basically what we, the property that we exploit here is this integer pair NM, which is the chirality of the CNT FET, then the diameter and the threshold voltage, all these 3 things are related. So this particular table here shows us that for different chiralities of carbon nanotubes, we have got different diameters and hence different threshold voltage, and hence we are able to use it in multi-valued logic kind of implementations. So now I'll come to the proposed designs. In the proposed designs, to start with, we have tried to implement a basic ALU, which is a arithmetic and logic unit. So this is a ternary ALU, and a ternary ALU built entirely using carbon nanotubes, so CNT FETs. So the first one is, what we have done is we've tried to propose a new architecture. So already there were 2 papers existing in literature that had talked about a 2-trit. Now trit is a new term, like it's like a digit, it's like a bit in ternary. So like a digit in binary is called a bit, in ternary it is called as a trit. So we are basically, it is a 2-digit ternary ALU. So we have tried to come up with a new architecture for this. So the existing architecture that was present was consuming a high amount of power. So we have tried to optimize in terms of power consumption and basically in the number of CNT FETs that were used to build the entire thing. So this particular TLU performs different kinds of functions. So there are arithmetic functions like addition, subtraction, multiplication, comparison, and there are 5 different logical operations, the basic ones: OR, NOR, NAND, NOR, XOR. So this particular design, the novelty that we got in was the function. Okay, so basically our ternary ALU consists of 3 sections. One is the select lines, like the select function generator, which selects which particular function you want to implement. Second part is a transmission gate logic, which connects the inputs to the functional modules. And third part, which is the main element, is the functional modules at the third step here. Functional modules are doing the major work of the ALU, which is calculating the functions, either it is a multiplication or addition or whatever it is. So in this, what we have tried to do is, for implementing the functional modules, we have tried to use a 2:1 multiplexer based approach. So there are different design approaches that are being used for ternary logic implementations. Like there are decoder encoder based approach, then there is a decoderless approach, then this is like 2:1 multiplexer is the novelty factor that we have gotten to get better power consumption. So this is the paper that we had published in IEEE Transactions on Nano in 2020 on the ALU. Now once the further on the ALU thing, as I said, the adder, subtractor, the multiplier, the comparator, everything was designed using 2:1 mux-based approaches, so that, in the existing approaches, there was a lot of power consumption due to the VDD to ground paths that were existing, so there was a lot of static power consumption. So by using a mux-based kind of approach, we have tried to improve the power in that way. And also, yeah, so after doing the ALU function, we have tried to go to ternary sequential logic. Now this is all combinational logic. So sequential logic, we have tried to give newer designs compared to the existing ones for sequential logic circuits, like basically a ternary D flip-flop and ternary counters. So the ternary D flip-flops that we have implemented, so this is the second paper that we had published. So there were 4 new designs for ternary D flip-flops using CNTFS that we tried to propose. So this first design was the novel one which had given us most power consumption, better performance. So here the novelty factor is like, it is like a basic ternary D flip-flop, but the first stage, instead of, normally the storage element in the D flip-flop is made of 2 back-to-back inverters. So instead of 2 back-to-back inverters, we simply replaced it with a buffer, and also we tried to design the buffer and the STI using a VDD by 2 based design approach. Like we took 2 power supplies of VDD and VDD by 2. That gave us better power. So that is how we designed the ternary D flip-flop. So along with the ternary D flip-flop, we also came up with other designs for like not using STIs, using successor predecessor circuits. Now what are successor predecessor circuits are? Like successor is a simple circuit which, for a 0, 1, 2, if the input is 0, it gives 1. For input 1, it gives 2. That is the next value gives the successor, and previous value will be a predecessor. So for a 2, it is 1, 1 it is 0, 0 it is 2, like that. So if you keep a successor and a predecessor one after the other, it is kind of it will give the same A. Suppose 0 is going to go to 1, 1 will go back to 0. So that is how the storage thing got implemented. So we used successor predecessor also, but the successor predecessor architecture was already there in one of the papers, but we try to give a better implementation internally in the successor circuit so that we could get better results. So then we also proposed 2 more designs in the paper called hybrid designs. Now in hybrid designs, what we did is we just interchanged the stages. Like in the first stage, we did a ternary buffer. Second stage, instead of STIs, we put successor predecessors. Similarly, in the third hybrid thing, we had successor predecessors in the first stage, and then we went to STIs in the second stage. So like that, we could make up, we could come up with 4 different designs and different architectures. And then what we did was we also used them to implement counters. So we implemented 3-trit counters basically, so which were running up to 3 bits. And so those also we used using each of the different flip-flops. So like that, we could get 4 proposed different counters also. So all the counters, all the flip-flops and all, we have included in this paper. Then we came up with, we saw a very recent paper on the CNT-FET based ternary memory circuit. So here they had implemented a ternary SRAM, which is a single cell SRAM basically, and like a normal SRAM will store a 0 and a 1, here it stores a 0, 1 and a 2. So it is like a ternary single cell SRAM that was implemented. This is the existing recent paper that we found. So this paper is also there in the transactions. So here what they have done is they have given 2 proposed designs. So they have used the SRAM by using, so basically in the single cell SRAM, what we do, the two main elements that we have is a storage mechanism, and there will be something for a read-write access. So read-write access are basically access transistors, and storage mechanism can be different things. Either it can be STI inverters back-to-back, either it can be buffer, either it can be successor predecessor circuits like I explained in the previous thing. So in the design 1 in this particular paper, what they have done is the storage mechanism is a successor predecessor thing, and the read-write is the transmission gates. But in the second design, they have used a ternary buffer so that instead of 2-stage thing, it became a 1-stage thing, and also it reduced the number of transistors that were used, and also the read-write access mechanisms were kept like the transmission gates itself. So this paper we have taken as base, and currently what I'm working on is I'm trying to implement a CNT-FET based ternary logic processor. So this is the current work of the thesis. Yeah, I'll be just wrapping up. So there are different logic or different blocks that I need to implement for this processor design as such. So I'm trying to implement a very small 3-trit processor. That means it will handle 3 bits of data, and it will have a 9-trit instruction code, and it will be running around 14-15 instructions. And I'll just skip this part and just go to the entire block diagram. This is a basic block diagram which you guys would have seen in the basic RISC-V thing. So basically, I want to construct a ternary instruction memory, a ternary register file, a ternary ALU. With the ternary ALU that I have already implemented, I want to extend it to a 3-trit one because I want a 3-trit processor finally. And then I want to, have a register file which will accommodate the 3 trits, and then a data memory, and then there will be some need of a control. So there will be a ternary control unit. There will be something required for a branching unit. So there will be a branching unit, and all that. Basically, what I'm trying to do here is I'm trying to put together the work of the ternary ALU. It was proposed in the first paper, the ternary sequential circuits that are there to implement registers we can be using, and then the ternary memory that is there in the literature, we can use it up to make a instruction memory, you can make a data memory and all that. So if you put together everything, and then we're trying to build a ternary logic processor for processing 3 trits of data. So yeah, this is what we're currently doing, and here are some results. The results are pertaining to the first 2 papers of mine. So the first results is basically for the TALU designs that were proposed. So here the improvement with respect to power and PDP was seen. So around 90% and 96% power PDP results improvement we could see. Also in the D flip-flop sections also, we have proposed 4 different designs, and the first design was showing very, very less power consumption, and also the PDP was like very less. So in order to conclude the whole thing, in this research work, we have shown that using CNT FETs, one thing I forgot to mention is all the simulations, everything I have done in HSpice used a standard CNT FET model that was given by Stanford. And with that model of CNT FET, I have implemented the whole thing in simulation level and cross-checked and verified using the functional simulations. Okay, so the basic research work was based on showing that using CNT FETs, a complete ternary logic processor can be implemented, and you can have different blocks of the processor that you can design. Then power efficient designs of ternary ALU and sequential circuits were also implemented. So and the current work, as I said, is building the ternary processor at the transistor level. Then an instruction set architecture obviously will be required in order to start with the whole processor design thing. So we'll have to come up with an instruction set architecture for the ternary thing. And then the proposed ternary thing will run a 3-trit data. And the power efficient multiplexer based approach that we had used in the TALU, we have planned to use for other circuits as well. So the future work of this can be looked at as, instead of a small 3-trit processor, we can go to an extended version, say 8-trit, 9-trit, 12-trit, 16-trit, like that. So yeah, that's all. Thank you so much.
Thank you, Sharwani. And now the next paper is on analog AI hardware and compute ecosystem for machine learning at the edge by Prateek Kumar from IISc.
Good afternoon, everyone. My name is Prateek. I'm a final year PhD candidate at Neuronics Lab, IISc Bangalore. And my research interest lies in pushing the boundaries of high-performance computing architectures for machine learning and AI hardware. So today I will be presenting on analog AI hardware and compute ecosystem for machine learning at the edge, where I'll briefly discuss about the exciting opportunities or the power of analog computing to significantly boost the performance of machine learning and AI systems. Okay, but so what actually I'll be discussing about is the sum of my work and some of the novelty that we have proposed here in this for the SRF. Plus, before that, let me say that why even do this research in analog AI computing for machine learning and hardware, and why it is so important in today's industrial context. What were the challenges associated with the analog AI computing that my research tried to overcome, and what is the impact of the research that I had been doing, and finally a quick demo of the product that we have built, and we'll conclude with the credits sections. I promise you I won't take more than 15 minutes, so just bear with me. Okay, so let's just start with a quick background. I think in the last 2 days we have already heard a lot of talks about why AI is required and different kinds of unconventional field of analog AI computing, whether it's a quantum computing or various other aspect, photonics. And analog is one such unconventional computing field where you explore the possibilities of, again, very, very high performance computational architectures. I'm talking about more than 1,000 times efficient than the conventional digital standard that industries have set. So that's the power I'm talking about. So, okay, let's make no mistake that today we are at the dawn of AI revolution, where everything from our social media to healthcare uses AI. And this is very challenging for the conventional hardware to build. The reason being, this is very challenging for the conventional digital hardware. The reason being, each AI algorithms do billions of calculations at the background, and each calculations requires enormous power and massive energy in execution. So let me give you an estimate. On an estimate training, one such GPT model takes electricity equivalent to yearly consumption by 3 households. And that's just to train the model once, and it generates carbon emission similar to what 5 cars would generate in their lifetime. And I'm just talking about just to train it once, right? And second, the resources required to train these algorithms are massive and huge. And this massiveness comes with the ability to cool the system. So if your area is more, you need more power to cool the system, your area increases. What if you can do the same computation in much smaller area and can do it much more effective? So this is where my research comes in. My research proposes an alternate domain of doing similar computation that we call analog AI computing. When I say, don't take my word, just look at the slides. You can see analog AI is almost 1,000 times more energy efficient than conventional digital design. But there are certain inherent challenges associated with the analog design due to which it has never taken off. So my research focused on overcoming those challenges and simultaneously prove you that AI can be used to design a large-scale AI system, analog AI systems. Right, so what are the challenges I am talking about? These are the specific challenges that my research addressed in the last 5 years of my PhD. The very first challenge is non-modular. Analog by nature is a non-modular design. What it means is, in analog, if you have to implement some function or computations, you have to do everything from scratch. You have to start from the transistor and then go to the system level. And you have to do this again and again. There is no concept of what we call the standard cells in analog. So those who are familiar with the digital might be aware that we have something called the standard cell libraries provided by the PDKs, right? And then you write a high-level code irrespective of which technology you work on, and it gets synthesized. That's fantastic, right? And it's actually do a rapid production. It has helped it. But in analog, there is no such concept of analog standard cells, because the designs and the parasitics starts varying depending on the technology node. And there is no concept of what we call noise margin in analog, right? And that noise margin thing is very important in digital, because it's provide reliability to the digital standard cells, but there is no such concept. The second thing is this: analog designs are not technology scalable. For instance, if I give you an example, most of the industrial designs in analog are built on 65 nanometer. And let's say tomorrow the industry tries to shift everything to the 28 nanometer or 7 nanometer. They have to do this everything from scratch, because specification changes and you have to change the aspect ratios. So it's very troublesome and very time consuming. So you cannot just port your architecture if you are designing 65 nanometer to 28 or other technology. You have to do everything from scratch. And the third is, analog designs are not bias scalable. It means you design an analog circuits or analog computational units, whether it's some machine learning, mathematical computational functions, or whatever it is. You design it for a fixed specification. You design it for either sub-threshold or above threshold. Let's say if you design a circuit in above threshold and you want to shift the design to sub-threshold, your functionality is going to get distorted. You're not going to get the same functional curve out of it. And last is, the biggest problem is analog designs are not digitally synthesizable, right? You have to do everything in custom, and it's a massive, massive pain. So, plus there is a challenge of programmability in analog. It's very difficult. In FPGAs or in digital, we have digital interconnect fabrics, which is basically a bunch of transmission gate that you program using some set of codes, even whether it's an FPG or ASIC, and you get the desired functionality. But that's not case. There is no such thing in analog. So these 4 challenges are major and preventing the design of analog hardware for large scale AI system. And that's what my research tries to tackle. So what we did was, I'm sorry for the audience sitting this side. So what we did was we proposed a novel analog computing framework that we called SAFE-based analog computing. What it means is we proposed a framework that helps you create the analog computational function just by focusing on a simple shape. And then you can use it like a Lego box to create a large scale AI system. I'll show you how. And the second is this framework allows the complete analog design to be fully process scalable and bias scalable. It means you design your architecture once, and irrespective of which technology node you are implementing, you can simply port your architecture from a higher to lower or lower to higher technology node. And then the architecture is fully bias scalable. You can perform the same architecture at different power and performance specification. Okay, and then we also introduced something called programmability in analog plus the concept of analog standard cells in that you can use irrespective of, again, which technology, which power conditions you are using. If certain conditions are satisfied, the whole analog system is going to be modular. So finally, we also added what we called a complete analog AI compute ecosystem, which consisted of a software stack plus the hardware-based analog AI chipset, and then there is a test framework. We just not focused on the processor because if we wanted to sustain this technology and do a kind of a startup, that the goal was that. So it's not just necessary to not sufficient to build a chip out of it or an accelerator. So you have to build a whole stack or ecosystem out of it that any person can use and then simply like synthesize the circuit design. So in briefly next 10 minutes, I'll present to you one of the project that we call the Hyderabad project. Hyderabad stands for Analog Reconfigurable Technology and Bias Scalable Hardware for AI tasks. And out of many projects that I have did, this one is very close to my heart because this resulted in India's first analog AI accelerated chipset. If you might have Googled it or you might have heard about it, you might have heard about it. So if you not just Google it, you'll find this is the India's first indigenously developed analog AI accelerated chipset. It's widely in media now. Right, so I remember I started this design in 2019. I joined in 2018 as a PhD student. I started this design in 2019, and we had this set of challenges to be solved. We started by creating a mathematical framework that is very robust enough to be used in analog computing. From the maths, we moved to the design of computational modules, and from modules we moved to the design of blocks, computational cores. We put multiple such cores in a chip to create an accelerator chipset. Then we designed interconnect out of a custom interconnect out of it. So that was about the chip, and then we shifted did the design of the compiler that can interface with the open source machine learning framework. Presently the integration is with PyTorch only. And then we also design a test framework that can test the chip once you get it fabricated. Because in analog, the test point is rapid and massive. You cannot just imagine testing the design. It's not like 100 transistor design. I'm talking about 5 million and 6 million transistors in analog. This is very difficult to test. So let's just do a quick dive in it in next 8 or 9 minutes. Okay, so I won't bother you with the glory mathematics. It's already available in the paper in TCAS. The second paper for the Hyderabad is already published in ZCAS. Third is submitted in, I think, JSSA. So this one includes some novel work as well. Okay, so the theory goes like this of Hyderabad. You start by creating a non-linear shape. Let me see if I can see the pointer. Okay, the pointer doesn't work. Okay, so the basic idea, the whole basic idea, I'll try to intuitively explain it in just half a minute or so. You start by creating any non-linear shape you want. Let's say this red curve shown in this figure number 1. Your first aim is to create this non-linear shape, and the framework allows you to create this non-linear shape as much robust as possible, it adds certain constraint into your design such that no matter what your biasing condition is, your design of this red one is going to vary only in this gray area. Now consider that that's what we called as a design margin. Now compare this with the noise margin that we have in digital. So the framework make sure that your design is going to be lying within this gray area. And once you have this robust design standard cells, then you can use a simple rotation, translation, and addition to create various non-linear complex functions required in machine learning tasks. For example, you can simply replicate, just flip this red curve and add this, so you will get this curve number C1, right? So this is just one example. And it's very good in analog that you can implement these kind of non-linear function using just like 8 or 10 transistors. It would take more than that. And the replication and the mirroring just come by using a simple current mirror, right? So I won't bother much about the circuit as well. I'll just give you a quick overview. That's the novel circuit. That's the only circuit that you're going to require in analog to implement all the complex computations required in machine learning. We have shown, so let's have a quick look at it. In figure 3, you can see what we call is N-type SSE or shape-based analog computing cell. It's a current mode parallel design architecture, those who are aware of analog. And one thing to focus is, look at this. So this is the only block that is replicating multiple times to give you figure number 1. So figure number 3 is actually giving you figure number 1. And then you have a mirrored image of this architecture that we call P-type SSE architecture. So the idea here is, once you build this SSE architecture, which consists of just one transistor, either NMOS or PMOS, and one diode unit or MOS implementation of the diode, you can use this module to create various complex mathematical function out of it. And the framework allows you to create this shape using this SSE module as robust as possible. Right, so I'll just a quick overview of all the works. For example, I'm just presenting few of the functions here. You see, just by using the simple SSE module, I am able to implement cosh, sin, ReLU, soft plus, sigmoid, tan, Mac unit, multiplication, DAC, everything can be implemented by using the simple SSE module that's already published. Right, and just to convince you that it works, we have also proposed the framework that you can create any other nonlinear function if it comes out in future. See, these are some of the results of the same circuit shown here. So the results are shown in the various technology node as well. I have not changed the architecture. The architecture is there in 180 nanometer. We have tested for 180 nanometer, 65 nanometer, 28 nanometer, as well as 7 nanometer. So this result is just at the two end of technology that we have access to. One is 7 nanometer and one is 180 nanometer. You can see the results are overlapping completely each other. Right. So that's what I was talking about, the process is scalability of the design. And then the modularity of the design. So what does it shows us? So now we have something called, so now my research proposed what we something called analog standard cells. Using a common SSE module, you can create all the complex mathematical functions, 78 functions we have shown in the paper, and the rest depends on your thinking, how we can use those framework to create those functions. So now you can use those functions as analog standard cells because those functions can be used throughout the technology node. Now you can compare this with the digital standard cells that you have. Right, and then irrespective of which technology you're working on, you can use this to synthesize, you can use this to implement your design in a particular technology. And then the third thing is very interesting. It allows the circuit to be bias scalable again. So let me give you an example to make it more clear. For example, you might have heard about Intel 12th generation or 13th generation processor. And they have something called, different cores they have. One is called PE core and one is called EE core. So energy efficient core or performance efficient core. And depending on the application requirement, the application shifts from PE core to EE core and vice versa. So now imagine an analog. You have a single core, not two cores, that by changing the biasing condition, you can use the same code to operate in high performance mode, or you can use the same code to operate in energy efficient mode. Imagine the power in the area that we're going to save. So that's the power of bias scalability in analog. And my research made it possible. So what we did, in sum up, we started with maths, we created the modules, and those modules are now working as a code. So each code has a scratchpad memory near it. It's a basic SRAM design. And then those multipliers, adder, ReLU, DAC, and memory, that is forming one code. And then when you combine multiple such code, this is what you get. This is a microchip photograph of the Hyderabad chip, which consists of 5 million transistors. And those who think 5 million transistors is less, let me give you an example. In multiplication in digital, it's going to take anywhere between 100 transistors to 1,000 transistors. In analog, you can do the same multiplication using 2 transistors. So even if I'm talking about a factor of 50, you multiply this 5 million transistors by 50 to have an apple-to-apple comparison. Right? That's going to be in billions. And you are able to implement that much computation in just 5 million transistors. So this is an internal architecture consisted of 8 high-performance computing cores. I won't go into the details of the result as well. But one thing I can point to, you see, in 180 nanometer, you can do in different operating regions, the multiplication, which consumes most of the energy, you can do in 190 femtojoule. That's already breaking state of the art here. Right, and in 7 nanometer, the architecture, it's like very much energy efficiency, 0.018 femtojoule. Right, just last 2 slides, I'll wind up. So, what else was done? As I said, hardware is not, again, enough just to propose the hardware. It is also essential to have a very good software to add on to the hardware, right? So we did not stop just by making the hardware. We started with the design of the compiler that could interface with the open source machine learning library called PyTorch. Currently, it has a few algorithm support, not more. And then it takes input from the machine learning algorithms. It maps into the SSE domain. It also takes inputs from the user defined specification, like at what power, what speed they want to implement their chip. It creates a binary files out of it and then map into the Hyderabad chip. That's the compiler part. And then again, as I explained, testing the chip was also a very difficult task we created by, and there was no such method available with the industries or anywhere. So what we did was we created our own test framework using open source Python script. So what does this test framework does is it integrates with all those glory test equipments that you have in your lab. You might have crores of test equipments you have, and then it takes into account one of the Python-enabled FPGA board. And irrespective of where you are sitting, you can simply write your test code in a high-level language, and you can just let it run. Your results will automatically get stored in your PC. Right, so just to sum up what we have done, so this is the kind of analog AI compute ecosystem I'm talking about. You start with an input library, input machine learning library, whether it's PyTorch, presently they're supported, and we are also now moving to TensorFlow as well. And then this machine learning libraries get mapped through your firmware, through a compiler. This is the compiler which do a fixed point quantization, creates a data flow graph out of it, and then it gets mapped to your Hyderabad chip. Hyderabad chips has a novel interconnect network, near memory computational tile. It can implement multiple activations function, and you can see the 8 computational core. And then there comes the works of test framework. The output goes to the PC, right? So this is the chip I'm talking about, right? So a quick demo here of 10 seconds. So these are the outputs of the chip. Instead of like bugging through all those table results, I just showed you the chip result. And this is the compiler that is running on the background at the network to show you this result, right? And what's my research impact? So now it's possible to create the analog standard cells that you can use to design large-scale AI systems, and your designs become now modular in analog, right? The design is also technology scalable, and these are some of the media works that we have. And finally, credits to my supervisors. So Professor Chetan, who is my thesis supervisor, and Professor Shantanu for USA. This is a collaborative work among both of them, and this is my end of the presentation. Right. Thank you.
Just before we break for the tea, the paper which is going to be presented before us is Design of Embedded Vision System based on Zinc SoC by Singam Venkatakrishna Pratap Reddy, Namburu Banabhushan, Paladugu Venkatesh, and Tirumala Krishna from JNTU UK.
Good afternoon, everyone. Today I am here to share about my project done on design of embedded vision system based on HICC SoC. My name is Singam Venkata Krishna Pratap Reddy. I am pursuing final year BTech in Lakkireddy Balreddy College of Engineering in Mailavaram, which is affiliated to JN2K Kakinada. So this is my project. This is agenda in my presentation. So I am not going to implement this ingestible capsule. I just work out the camera inside this ingestible capsule. So I am going to implement this camera with the FPGA. In some papers, this embedded vision system is implemented by using CPU and GPU. Rather than using CPU and GPU, using FPGA, it increases more performance and more flexibility. Rather than using CPU and GPU, using FPGA, it's more better. Then this is overview about my project. So that is FPGA board that is interfaced to OV7670 camera. Then by processing some creation of projects and all, then the output will be get. So to interface camera with the JET board, we use peripheral module which is present in FPGA board. By connecting the camera to the FPGA board to peripheral modules, in this I use OV7670 camera module. OV7670 camera module is CMOS image sensor which has photosensitive array of 640 by 480, and it flexes images at 30 frames per second, and it has 0.3 megapixels. So in this I use Vivado and Petalinux to implement this embedded vision system. So nowadays smart world requires embedded vision systems with optimized design matrix. Optimized design matrix means low cost, high performance and high flexibility, and low area, time consumption is less. So I implement embedded vision system for medical applications. So I take the problem from transnal endoscopy. Transnal endoscopy means in transnal endoscopy, fiber cable is used to detect diseases. So this fiber cable thickness will be 6 millimeters. At the one end, the doctor will see the condition of the patient. At the other end, the camera will be present. That camera will give images to the doctor. So by using this transnal endoscopy, doctor cannot be seen the images of patient clearly. Yeah, it also takes long time to perform. So this is the ingestible capsule. In this ingestible capsule, this is the vision. So I implemented this embedded vision system. So this capsule is injected into the patient body. That that camera will detect images and shown on the PC in continuous manner. It is painless method, and it is very helpful for doctor and patient. Doctor can be seen images very clearly. So this is about this length is about 11 millimeters, and this is about 27 millimeters. This ingestible capsule consists of with camera. It also consists battery and transmitting antenna and receiver antenna at the wrist of the patient. So by transmitting antenna sends the images to the receiving antenna. The belt which is at the patient wrist, the recorder records the images which is sent by the transmitting antenna. So This is the block diagram I implement for embedded vision system. This is application for vision. Operating system uses Linux OS and hardware platform is used Vivado. I use FPGA board to configure FPGA, that is Z board. Hardware platform Vivado is used, and to boot SD card Linux OS is used. After interfacing the OV7670 camera module to the Z board, this Z board and OV7670 camera module works on client and server model. In this dynamic host configuration protocol application runs. So as Z board requests image from OV7670 camera module, OV7670 camera module sends images to Z board. Then Z board sends this to the PC by using Ethernet. So to booting SD card and to configure Z board, this is the hardware platform and that is the software platform I use. So in this Vivado, we use files for camera to build inbuilt camera. So in that create block designing, we add sources for OV7670 camera module by using VHDL and Verilog coding. After creating OV7670 camera module, by taking Jing 7 processing system, block design will be created, and then for that block diagram, generate bitstream file. After generating bitstream file, it can be exported to software development toolkit. In that kit, we select configure, and in this file, for application, executable link formatable file will be created. So this is used to configure Z board, and Linux OS is used to boot SD card. In that Linux OS, so we create project, and by creation boot file, in that boot file consists of a hardware file, bit file and ELF file. These three files consist in boot images. So by processing all, SD card is booted. So this is the execution results. This is LUT lookup table, flip-flop units and BRAM and input-output conditions. This is after synthesis. This results after implementation. After implementation, it runs optimized design matrix. So lookup table is reduced from 4% to 3%, and using RAM also will be reduced. So in this way, output is displayed like this. So camera detects to that PC images will be displayed on the screen. Like this way, in that this embedded vision system is placed in that capsule. That capsule is injected into the patient body. That streams around the intestine of patient. Then that images will be displayed on the screen. So these are the findings. So predicted diseases, small intestine and examine esophagus. In perspective of doctor seen images very clearly and with a high. So working of capsule images, detect images and showing on the screen in continuous manner. So these are the optimized design matrix which is getting from the project. So low power is about 1.698 watts, and high efficiency, high flexibility. Execution time for this project is 40 milliseconds. High resolution of camera. So vision system I implemented for medical applications. This can be also used for many applications like home automation, security, traffic controls, and in also in vehicles. So thank you.
Yeah, thank you. So we can take a break of quick 5 to 10 minutes and we'll assemble back. So we have 3 papers to go. So maximum by 4, 5, we will start the session. So welcome back. So we will have now the presenter of the paper, Device Modeling of Oxide Thin Film Transistors by Ashima Sharma, Pyati Ganga and Manisha Bharati from NIT Delhi. So please welcome her. Let's have a round of applause for her.
A very good afternoon to everyone. My name is Ashima Sharma. I'm working as research scholar in National Institute of Technology, Delhi. I'm here to present for Student Research Forum on the title of Device Modeling of Oxide Thin Film Transistors. This is the outline of the presentation, starting with overview, problem statement, scope. Then we discuss about the proposed solution methodology, followed by results and conclusion. Overview. MOSFETs and TFTs. Despite being structurally different, but they both belong to the class of field effect transistors because the drain current in them is controlled by the bias voltages. MOSFETs, as we all are aware, are the vital components of IC technology, where the main emphasis is on designing the high-performance devices at considerably high processing temperature. But for the large area electronics or for the display application, the processing temperature needs to be low. And that is where the TFT come into play. That is the difference between the MOSFET and TFT. As we can see, the substrate type of the MOSFET is the silicon wafer, while for the TFT, it is glass to accommodate the display application. But nowadays, for the flexible electronics, we are now using plastic or paper as the substrate. In the MOSFETs, since the substrate is silicon wafer, which is a type of semiconductor, that is why the channel is induced in the semiconductor layer through the mode of inversion. But in the case of TFT, since the substrate is glass, plastic or paper, which is a type of insulator, that's why the channel cannot be induced, and that is why a thin film is deposited on the substrate. That's why the name thin film transistor. And the mode of operation is accumulation for TFT. The processing temperature for MOSFET is around 1000 degrees Celsius, while that for TFT is around 600 degrees Celsius. And even now, room temperature fabrication is also possible, depending upon the semiconductor layers. And the application for MOSFET is high-performance devices, while that for TFT is OLEDs or LCDs. So we can say that TFT is not the alternative to MOSFETs, but it comes into play where a crystalline-based semiconductor cannot provide a fit. So depending upon the type of the semiconductor layer of the TFTs, there are the different type of TFTs. That is the amorphous silicon TFT, organic one, polysilicon, and amorphous oxide semiconductor TFT. So earlier we used the amorphous silicon or the organic TFT to design the LCDs because they have the good mobility and they have the good uniformity. Because of the good processing temperature and the good uniformity. But since the mobility is low, they cannot be used to design the high resolution displays, or they cannot be used to design the OLEDs because OLEDs are current driving devices. Also for the polysilicon, we can see it has the both types of polarity present, like the N type and P type, and it has very good mobility, but it has the uniformity issue because the polycrystalline structure, that is why it suffers from the grain boundary problem, and it causes the serious Mura problem, unevenness illumination in the OLEDs. That's why we are switching towards the amorphous oxide semiconductor TFT, which offers the exemplary characteristics, good mobility, good processing temperature, and due to the large band gap, it has the high transparency to visible spectrum. And that is the choice of material for the TFT in this presented work. So why do we need the device model of the oxide TFTs? So every chip every chip design industry has basically two worlds. One team is known as the fabrication or process development team, and another team is known as the IC design team. So the fabrication or process design team is associated with making of transistor through the complex processes like lithography, diffusion, ion implantation, and all. And then there is the IC design team, which uses this transistor and make the network of the transistors to perform a specific function. So that's why this compact model or device models comes into picture, which acts as a bridge between these two teams. It is basically the computationally efficient description of the device in terms of its terminal voltage and currents. It has the IV description of the transistor, and it is fed inside the simulator engine. So the requirements for a good device models are, first of all, is accuracy. The error between the measured and the model outcome should be less than 5%. It should be computationally efficient, because when we are designing the complex circuit, so the IDS is calculated a lot of times. So simplicity versus accuracy, there is always a trade-off. And it should involve some physical properties as well. Okay, so lot of models, they are based on the table lookup type or the neural ones. But it should have some physical properties so that the scope of the model can be enhanced beyond the dataset boundaries. And also it can help while the troubleshooting. And it should be continuous over the wide operation region, otherwise we can have the convergence issue. And it should validate the benchmark test and should be scalable for different aspect ratios. So AIGZO TFT, it is a class of amorphous oxide semiconductor TFT only, but it has gained the enormous consideration since its room temperature fabrication in 2004. Due to its exemplary characteristics and advantages it offers, the primary application of the TFT, which was earlier OLED and LCDs only, has now pervaded into the different domains like wearable, flexible, health monitoring systems, smart packaging or self-contained electronics, RFID tags, or high-resolution displays. Since this technology is still in its progressive phase, the limitation with the technology is that it lacks the standardized CAD tools to design these circuits. That's why the proposed solution is the device modeling of oxide thin film transistors, which is divided into 3 phases. First of all, we develop and validate the oxide TFT models. Then we accommodate the model with the short channel non-ideality so that our circuits could be designed with any aspect ratio, whether short channel or long channel. And then we further enhance the scope of the model to predict the temperature dependent characteristics as well to make the model complete. The first phase, this is the basic methodology that we have used. Here we have the micrograph of the TFT. In our CENIMAT lab in Portugal, we got the measured data from this fabricated TFT. And using this measured data and the input parameters, which are just the device dimensions and a few electrical characteristics, we use the device equations and the input parameters to extract the unknown parameters of the device using the LSU curve fit function in MATLAB. And these extracted parameters, they are again and again fed into the optimization routine until the error between the modeled and the measured outcome is less than the 5%. Only then the model is termed as viable for circuit designing. Once the model is ready, then we implement it in the Verilog A and fed inside the SPICE simulator engine, and we make its symbol as it is shown to design the circuits for quick instantiation of the circuits. We have used the Cadence Virtue simulator for that. This is the device modeling equations. The detailed expression is given in the paper, is already published in the paper. Here what we have done is, the basic characteristics of the device, they are divided into 3 regions, 1, 2, 3. In region 1, deep states prevails. In region 2, tail state prevails, while in region 3, the band state prevails. And depending upon the specific attributes of the operating region, different device physics dominates in that particular region, and based upon that, we have calculated the drain current in all the 3 regions. So from equation 1 to 5, we calculate the IDS current for the device. So once we have the device, we have developed our device model, then we validate it. For the validation, what we do is, this solid line denotes the measured characteristics, and these circles are the model outcomes. So we compare the measured characteristics with the model outcomes for both output and transfer characteristics. Since we can see there is a good accuracy between the two, the error between the two is less than, is found to be around 2.6%. So this model is found to be optimal for circuit designing. Also, the inset of these two graphs shows the first derivative of output and transfer characteristics. Their good accuracy shows the continuity of the model. So once the model is designed, then we extend its scope to design the short channel non-idealities. Okay, so the channel length is vital aspect for designing any circuit. And when the channel length is shrinked beyond a certain point, then the electrical characteristics of the device are always affected. That's why the long channel device model cannot be directly adapted to the short channel length devices. The short channel non-idealities must be taken into account. Here we can see the normalized characteristics of the IGZO TFT. It is not overlapping. As the channel length is reducing from 20 micrometer to 2 micrometer, we see the reduction in the current for both output and transfer characteristics. This is due to the presence of contact voltage drop in the short channel devices, which is taken into account. This contact voltage drop, which is due to the Schottky barrier at the contact electrode, is drawn against the VGS and VDS of the device and then formulated in terms of the mathematical expressions. So to accommodate the effect of this potential drop into the model, we can enhance its scope to design the short channel and devices as well. Here we can see that earlier, when we didn't apply this VC component, the solid line was our measured characteristics. Here we can see that it is overestimating the drain current. But after incorporation of the VC parameter, the contact voltage drop, which is present in the short channel and devices, we can see that the measure and the model outcome, they are in close proximity with each other. So this is the model validation for short channel and TFTs of 2, 5, and 10 micrometer. Then after, this is the last aspect, we enhance our model with the temperature characterization. So for the real world applications, the circuits, the complex circuit should predict its response for different temperature regions. So when the temperature is varied, we know that the electrical characteristics of the device are also varied. Here we can see as the temperature is increasing, the current is also varying. Here we have just shown the temperature varying parameters. We can see the on voltage, percolation voltage, and the field effect mobility. Due to the thermally activated behavior of the device, it triggers the carrier from its local states and non-local states. That is why on voltage and percolation voltage, which we say the starting voltages of the device, they decreases, and the field effect mobility of the device, it keeps on increasing. That is why the current is increasing as the temperature is rising. Also, it is moving towards the left because V1 and Vp are decreasing. So it is comparatively easier to take into effect the V1 and Vp, but this mu Fe, which is a function of temperature, this mu Fe is also a function of gate to source voltage as well. So if we need to thermally characterize our model, we need to take the 2D effect of the mobility with respect to temperature as well as the gate to source voltage into account. So this field effect mobility for the different VGS is given by equation 8, where P and gamma are the empirical parameters. So by noting the trend of P and gamma with temperature and deriving the mathematical expression for the same, the mu Fe becomes a two-dimensional function of VGS and temperature. This is the methodology for temperature characterization. For this, what we have done is, first of all, we have segregated our device into two terms. One is the device-based parameters, and one are the temperature-based parameters. Okay, so for the base temperature, which is the 25 degrees Celsius, we extract our device-based and both temperature-based parameters. And for the different temperature ranges, we keep our device-based models to be exact, to be intact, and we only extract the temperature-based parameters. And then we try to see the trend of these temperature-dependent parameters, and we see that these parameters, they follow the Arrhenius law. Then we formulate them in terms of the mathematical expression and include in our model. So once we have, after formulating all the mathematical expressions, the model is validated, we can see the measured and the calculated response for output and transfer characteristics of the device for varying temperature ranges is in good accuracy. The average percentage error is found to be less than 2.5%, which is optimal for circuit designing. And further, to reinforce the model's accuracy, the whole model's accuracy, what we did is, we then implement this model in the Verilog A, then fed it inside the Cadence Virtuoso, and then we simulate 11-stage ring oscillator. And then we just compare its performance with the fabricated 11-stage ring oscillator. The accuracy between the two reinforces the model's validity. So in conclusion, we can say, if any device is new and we want to design any new circuits, complex circuits from that devices, so we need the compact model for the same. Here we can say we started our journey with the basic transistors and its characteristics, and we have developed the self-contained electronic circuits by first developing the model for the long channel devices, accommodating it with short channel TFTs, and then enhancing its scope with the temperature characterization. These are the references, and the detailed analysis is given in the last 4 published papers. Thank you so much. Thank you.
Thank you, Ashima. So now I would request the team to come on and give us the paper details of evolvable hardware-based approach to design fault-tolerant control circuit for FPGA-based design by Deepanjali S. and Dr. Noor Mohammad, IIT Kanchipuram. Please give them a round of applause.
So good evening all. My name is Deepanjali. I am from IIIT DM Kanchipuram. I am a PhD scholar under project category, and my project is funded by DRDO. And the title of my research is Scalable and Accelerated Evolvable Hardware for Fault Mitigation in the Control Circuits of FPGA-based designs. This is the agenda of my presentation, and the main motivation of this research is like, when any digital electronics are going to be deployed on a harsh environment like a nuclear reactor or any space-based mission, there are high chances of radiation-based environment. And these faults are going to be called as the single event effects. And any digital electronics as such, if we speak, it mainly contains a control system and the other data or arithmetic units. So when this kind of error is going to mainly occur in the control circuit, there are high chances of getting a functional failure or a mission failure, because from the control circuit is where the control signals are going to reach the arithmetic circuits. So there is a high requirement for creating radiation hardened control circuits, either in the fabrication level or in the system level. And the main thing that we are going to focus is how in a system level we are going to give this fault mitigation. And so if you see among various techniques that can be used for fault mitigation, one of the evolving area is the self-healing electronics. So if you put a Venn diagram where computer science, electronics and bio-inspired algorithms are going to come, then biotronics or self-healing electronics is the combination of all these 3 Venn diagrams. And when talking about self-healing electronics, the major requirement is the reconfiguration. So the electronics should have the capability of reconfiguring itself from a faulty mode to a non-faulty mode. And in FPGAs, which is a reconfigurable platform, the major reconfiguration techniques that are available is dynamic partial reconfiguration. So many commercial FPGAs like Xilinx, they provide DPR tools, which is called as dynamic partial reconfiguration tools, and there are ports which can access the configuration bit stream. But in FPGAs, which are going to be used for a military space, then the bit streams are going to be encrypted form to protect from reverse engineering. So if we take among these two reconfiguration technologies, the native reconfiguration, that is the DPR method, has reached its maturity. But where if you come to the other reconfiguration technology called as virtual reconfiguration techniques, it hasn't reached the maturity level. And while talking about self-healing algorithms which are going to be deployed on this electronics, we are going to mainly focus on evolutionary algorithms. And this evolutionary algorithms, as such, if you take, the search space is going to be huge when we are going to consider a complex circuit. So the main motive is to create a scalable and accelerated evolvable hardware so that the fault mitigation time is going to be less. And among the various fault mitigation systems, we are going to focus on a system level mitigation, and in general, or the one which is sort of more used is the redundancy methods. So if we have a circuit, say A, then a copy of A will be made twice, and we will have a majority voter which will vote the two best outputs. So here if you see, the area power is going to be the cost of it. So to overcome these challenges, we are going to go for bio-inspired algorithm, and this evolvable hardware, where we are going to deploy an evolutionary algorithm on the hardware, is going to come under the area called phylogeny. And while talking about fault-tolerant electronics, these three are the main parameters which has to be taken into account to show the efficacy of a system. And the related works are like the main circuits which are going to be adapted to the fault-tolerant environment which were done in the related works are quadrature decoder, brushless DC motor, and a decoder, 8-bit parity checker, and a multiplier. So among this, the control circuits are the quadrature decoder and a brushless DC motor. So this brushless DC motor is the only circuit where virtual reconfigurable circuit was used. So we have taken this brushless DC motor control circuit, and we are going to deploy our evolutionary algorithm, simulate the errors, and show the efficacy of our system. And so coming to this implementation, so why we are going to take this brushless DC motor control circuit is, this brushless DC motor is used as actuators in many flight control systems. And it is also used in navigation control of many rovers in the space. So that is the reason why we have chosen this brushless DC circuit. And this is the main state transition table, or the functionality of the circuit, where the positioning signals are going to be the input and the driving signals are going to be the control signals. And from this table, we are able to map what is the functionality in the terms of Boolean expression. So from Q0 to Q5, which is the control bits, the expressions are given. And this particular virtual reconfigurable circuit itself has two main components in it. One is a configuration register, another is the two-dimensional it is a reconfigurable structure. And if you take this two-dimensional structure, we are going to have a multiplexed mode. So this multiplexed mode circuit is going to be controlled by the bits that is stored in the configuration register. So based upon the values in the configuration register, the reconfiguration, that is the routing structure and the functionality of the circuit, can be reconfigured. So what is going to be the input to this evolutionary algorithm is the things that are going to be stored in the configuration register. And to represent this brushless DC circuit using a VRC architecture, we need a 6 rows and 3 columns architecture, and each each programming element in this architecture is going to made up of three multiplexers. So these two multiplexers are going to accept the external input, and one mux is going to accept the function. So based upon the values that are stored in the configuration register, the inputs are going to be accepted, and based upon the values that are selected from the input, it is going to be passed to the function block, where the gate level gates are going to be implemented, and from that the outputs are going to be selected using the select line which is stored in the configuration register. So the main thing that has to be noted here is in the configuration register. So this is the search space which I was talking, and this bits are what is going to be sent to the evolutionary algorithm. So if you take here 135 bits in total of adding all the multiplexer select lines, we are having 135 bits. And in terms of architecture, if you see, the number of multiplexers are 54. So there is a main need to reduce the search space and the architecture. And this particular structure is going to be adapted from the self-repairing control circuit of brushless DC motor, which was already presented in the NASA conference. So the same circuit is taken in our work, and these are the problem statements or the challenges which were found. So in terms of architecture, so if you see a simple control circuit which is having 3-bit input and a 6-bit output is going to have 135, that is 2 power 135 is its search space. So the architecture is going to be huge. It has 54 multiplexers. So the first idea is to reduce the architecture, and the second idea is to reduce the search space, so that 135 bits, how we are going to reduce it, and in turn, how after reducing the search space, the convergence of our algorithm is going to be increased, accelerated. So the scope is like, we have taken the circuits which are going to be used which is used in the space missions. So in that point, we have taken brushless DC motor control circuit, which is already implemented using the same methodology, as well as we are taking a RISC-V5 processor control circuit and a rover straight line navigation control circuit. So these control circuits are where our proposed methodology will be tested. And the first solution is like how to reduce the architecture. So in the previous architecture where 6x3 architecture was used, we are reducing it to 6x1 architecture. That is, the column has been reduced. So here, if you see here, after understanding the phenotype, the term phenotype is nothing but the circuit or the part where you are going to apply the algorithm. So here the phenotype is the circuit. So after understanding the circuit, we have removed some redundancy in the circuit, and we have achieved this 6x1 architecture. And because of reduction in the columns, the number of multiplexers have been reduced to 12. So this reduction is mainly seen by removing the redundant NOT gate as a one from the apart from the VRC architecture. So if you see here, there are 6 programming elements, whereas in the previous case it was 18 programming elements. So from 18 programming elements, we have reduced it to 6 programming elements, and each programming element will have 2 multiplexer, only to accept the input. And the multiplexer which was used for the function is removed because the NOT gate that is the redundancy in the NOT gate has been brought outside the VRC architecture. And because of this, the configuration register, that is the search space which we were talking about 135 bits, are reduced to 36 bits. And another solution which we were thinking is like, for example, if we have some fault in our in our biological system, and if we exactly know that the problem is in our hand, and if we go to a doctor, he says like, you have to take a master plan, then that is something which is absurd. So what we know is, if we are able to locate the error without going for 36-bit search space, if we are able to more locate the error, then still the search space will be reduced. So the idea of that has been proposed in the second solution. So in the second solution, what we did is, all the 36 bits which is going to be stored in the configuration register, that were induced with errors. So this induced error positions are given here. So 0 to 35, are the configuration register bits, and each bit is going to be given a flip in its bit. That is 0 is made to 1, 1 is made to 0, because of which the routing structure or the functionality structure will be changed. Once after doing that simulation, we were able to see that this position and the output bit has some pattern in it. And after studying the pattern, we were able to give this formula where a window will be restricting the configuration bit from 36 bits to 6 bits. So this is the formula which will be used to restrict the bits, that is E into N. E is the erroneous output bit. For example, if you see, if Q3 in my output, if Q3 is the error, so I can take this bit position and multiply with the value of N. N is nothing but the configuration, the length which is going to be given as the configuration for each programming element. So 3 into 6, 18. That will be the starting address of the window, and the ending address of the window will be given by E cross N plus N minus 1. So 18 to 23 can be restricted. So instead of evolving all the 135 bits, giving it to the algorithm, we have reduced it to 36 bits when the architecture improvement was made. And from 36 bit, we were able to improve it to, we were able to restrict and constrain the configuration search space to 6 bit. So this will be the proposed block diagram. And if you see here, in most of the cases, the algorithm, the computer science or the evolutionary algorithm which I was talking, will be deployed on a processor on a SoC-based FPGA. But whereas here what we are doing is, we are going to deploy all the models in the, all the models of the evolutionary algorithm, like fitness evaluation, random population. I'm not giving the details of these computer science related algorithm because I thought it would be more efficient to talk about the electronics side. So whatever is the modules that are present in the evolutionary algorithm, that has brought into the hardware side. So this will be the VRC circuit, and this will be the configuration register. So from the configuration register, the frame encoder will restrict the frame size. After the frame size is being given, it will be given to this length will be given to random population. So since random population fitness evaluation was all coming, that is why we had to reduce the search space. So if we are reducing the search space and applying it to all the modules which are given in the hardware, we will be able to give the acceleration in a higher speed. So this is the main result. So if you see the existing system, the architecture is 6x3, whereas in our proposed system, after removing the redundancy in the phenotype, we were able to get it as 6x1, and because of which the multiplexers were reduced from 54 multiplexer, we were able to get it to 12 multiplexer. And the chromosome length is also reduced to 36 bit, and if we use window-based method, then it is further reduced to 6 bit. Because of this, we were able to get the generation, that is, generation is nothing but after how much iteration we will be able to get the error. So if in the existing system, if we are getting the minimum generation as 3318, we were able to get the generation in 2 generation, because in the previous case, in the existing system, it was 2 power 135. Whereas in our case, it is going to be 2 power 6. And also, if you observe this graph, which gives the convergence parameter, it is going to be talking about different control circuit like quadrature decoder, brushless DC motor, navigation robot, and RISC-V processor. So if you see here, the fitness value, which is going to be given in the algorithm, is keep on increasing. So this values are nothing but given in the percentage. So if you see here, based upon Goldenberg's schema theorem, which is efficient for evolutionary algorithm, the fitness value is rising increasingly. So if you see here, also in the proposed system, we were able to reach this fitness, 100% fitness in a quite lesser generation. And this is the resource utilization. So if you see here, on an average, in the LUTs and in the terms of registers, we were able to reduce, on an average, we were able to reduce the resource utilization to 36%. And also, if you see here, both, although we have taken up the single event upset as the motivation, we were able to go for multi-bit upset also. So at each, for each control circuit, we can able to see that we are getting 100% efficiency if the fault is going to be in the input select line and if it is going to be in the function select line. And in each case, we have also given the minimum generation and maximum generation. The minimum generation and maximum generation is like, if you are going to do the trial for 10 trials, that is, the same algorithm is going to be run on the same circuit for 10 times, what is the minimum generation which is required, what is the maximum number of generation that is required. And what is the fault recovery time for the circuit? So based on this formula, if you see here in the existing system, we were the fault recovery time is 37.92 microseconds, whereas in the existing system it is 4.96 microseconds. So in all the three levels, in architecture, in the representation, in the convergence, we were able to show some improvement. And in the existing VRC, 89% of multiplexers were used for a particular FPGA, whereas in the proposed VRC, we are reducing it to 36%. And with respect to representation, if for the brushless DC circuit, if it is 135 bits, it is going to be reduced to 6 bits, and because of which the convergence also has increased. So as a conclusion, I would say that the main contributions were moving for extrinsic evolution to an intrinsic evolution, where all the algorithms of the evolutionary algorithms were brought to the hardware. And in terms of architecture and in terms of representation, we were able to show the improvement, because of which the convergence has been accelerated. And in the this proposed solution also will be implemented for certain benchmark circuits. And this particular content, which was given as logic level evolution, is also has been sent to Journal of Electronic Testing, and it is published. Thank you.
Thank you, Deepanjali. So finally, we will have the paper on improving endurance of non-volatile memories using compression, encoding, and selective victim catching by Ajit Nath and Hemangi Kapoor from IIT Guwahati. So please welcome him.
Good afternoon, everyone. My name is Arijit Nath. I am a PhD student at the Indian Institute of Technology, Guwahati. And I am about to submit my thesis. This is the overview of, I will give a overview of my thesis in this presentation. The title is Improving Endurance of Non-Volatile Memories Using Compression, Encoding, and Selective Victim Caching. So this is the outline of my presentation. I will start with introduction. Then I will give a brief introduction to all my thesis problems and their solutions. Then experimental setup. Finally, proposed techniques, along with a brief overview of my result. I am keeping the results short because of the time constraint. And then I will conclude my presentation. So with the advancement of semiconductor technology, the size and cost of the transistors have dropped down significantly. It facilitates the introduction of a large number of functional units, or in short, cores, within one processing chip. Hence, it also facilitates the execution of a large number of data-intensive workloads. And these workloads tend to show some typical behavior, like they have large working set data and low locality of reference. Because of this large working set data, it is very difficult to fit all the pages belonging to these applications within the limited cache memory space. And also, since the locality of reference is very low for the new applications like streaming application or the convolutional neural network applications, they tend to show a very limited locality of reference, and therefore, since the caches are based on temporal and spatial locality of reference, therefore the violation of these laws lead to a huge amount of cache misses, and these cache misses appear in the form of a large main memory access in the form of read and write accesses. The conventional DRAM-based memories, which are used predominantly to build the main memory, are suffering from high refresh energy consumption and poor scalability issues. Therefore, at this need of the juncture, we need memory that are energy efficient as well as they are highly scalable. The currently emerging non-volatile memories like STT-RAM, PC-RAM, and ReRAM are considered as potential candidates for replacing DRAM in the main memory layer. Obviously, these memories shows low leakage power consumption and high density, which are highly desirable feature in order to build large capacity memory and energy efficient memory systems also. But the advantage, there come certain disadvantages along with these advantages that cannot be underestimated. For example, these memories tend to show a asymmetric read and write behavior, where the write operations are much costlier in terms of latency and energy consumption. That means we need more latency to write to perform a write as compared to the read. Also, the writes are energy consuming. Furthermore, if the writes are confined to only one region of the memory, suppose if we are repeatedly writing to some specific locations of the memory, these energy intensive write operations also tend to degrade the lifetime because the cells wear out much faster as compared to the other cells that are not exposed to frequent writes. It leads to a degradation of memory lifetime, or in short, we say that these memories have a very limited lifetime. Furthermore, the non-volatility feature of these memories enable the data to be stored for an indefinite amount of time, and taking the advantage of which many malicious attackers or intruders, they can simply read out the sensitive information which are stored in the data and perform an attack. Therefore, this data has to be protected using some scheme like encryption. Encryption is probably the best scheme, but again, encryption introduces high randomization in the generated data block or in the encrypted data. And when we write this encrypted data in the memory space, it leads to a huge amount of bit flips. These bit flips are tiny write activities, and they also tend to degrade the memory lifetime. Therefore, write management in non-volatile memories is highly essential to improve its performance as well as to improve its lifetime. So in my thesis, I have proposed solutions to improve the lifetime of non-volatile memories using write reduction technique and wear leveling technique. So in write reduction technique, we talk about reducing writes at two granularities. The first one is coarse granularity. That means I try to reduce the traffic between the last level cache and main memory by giving some architectural solutions. And the second one is fine granularity write reduction, where I propose solution to reduce the bit flips, which are fine grain write activities that are happening in the main memory. The second approach is wear leveling techniques, where the writes that are happening to only one region of the memory are distributed uniformly across the entire memory space, so that the chance of failure of individual memory cells are reduced significantly, and it helps in improving the memory lifetime. So this is the overall aim of my thesis: enhancing endurance of non-volatile memories by coarse to fine grain write reduction and intra-line wear leveling. So in the first contribution, it talks about reducing PCM writebacks, where PCM is the non-volatile component in a DRAM PCM-based hybrid main memory, where one small part is of DRAM and it is associated with a relatively larger portion of PCM, and we reduce the traffic from last level cache and main memory by introducing a small layer of cache called victim cache. And it is called selective victim caching that I will explain in the subsequent slides. In contribution 2, I have proposed a compression algorithm and an encoding scheme to reduce the bit flips in PCM-based main memories. Also, I have proposed an intraline wear leveling that uniformly distributes the bit flips within the memory line. That's why I call it is intraline wear leveling. The third contribution is providing protection to the main memory data through encryption. And here we try to minimize the encryption-initiated bit flips by using a scheme called partial encryption scheme. Here we eliminate the encryption of certain frequent words that occur frequently across the memory space. Finally, the fourth contribution is about lessening the effect of bit flips in encrypted PCM, utilizing the effects of compression and encoding techniques. So these are my simulation setup. Here I have conducted my experiments using a GEM5 NVMe-based full system simulation framework. And the benchmarks I use are Parsec 2.1 and Spec 2006 benchmark suite. And we have carefully selected the benchmarks based on their read and write intensity behavior. And for calculating the energy parameters for caches, we have used Cacti and NVSIM. These are the different parameters that I have used for my experiments. So I will now go to my first contribution, which is reduction of writes using selective victim caches. So here I have used a small layer of cache, which is fully associative in nature between the last level cache and DRAM PCM-based hybrid main memory. The main idea is to reduce the traffic towards the PCM section of the main memory because these writes are costlier as compared to the DRAM section. So here I put the evicted blocks which are evicted from LLC before writing them into main memory. But see, since victim cache is a very small resource, it cannot accommodate many blocks. Therefore, we carefully selected the blocks which are critical to performance, and we allow the other blocks to go to main memory. So what are the critical blocks, and how do we define the critical blocks? It is defined, or it is selected based on reuse distance. And we say that if a block has a small reuse distance, and if it were used with small reuse distance for a large number, with a high frequency during its LLC residency, then even if that block is evicted from LLC, it has a very high chance that it will be reused again in the upcoming memory references. So we select those blocks and allow them to be stored in the victim cache. Now, to further reduce PCM writebacks, we propose two policies. The first one is victim cache replacement policy. It works on the replacement policy of victim cache that prioritizes the eviction of a DRAM block rather than a PCM block. So here we scan the two LRU position in the victim cache, LRU and LRU -1, and try to find a DRAM block. If we find a DRAM block, even if it stays in the LRU -1 position, then still we will evict the DRAM block to keep the PCM block. So this is the overall policy of victim cache replacement policy. The second one is prioritized partitioning of victim cache, where the victim cache is partitioned with unequal partition, dedicating a small share to the DRAM blocks and a relatively larger portion to the PCM blocks. So idea is to keep the PCM blocks for longer duration in the PCM partition. However, we have created a small partition for the DRAM blocks because we also try to store the critical DRAM blocks, because the eviction of such blocks might hurt the system performance. So the block went to the DRAM partition, and the corresponding block was evicted from the DRAM partition to the main memory. So these are the overall results associated with this technique. We get significant improvement in PCM write reduction and the corresponding improvement in performance, which is measured in terms of cycles per instruction, or CPI. These are the area and overhead, storage overhead. This work was published in ACM TODAS. Now for the second work, this is wear leveling and adaptive encoding compression of frequent words in non-volatile memories. So here we have proposed a compression scheme. So why compression is needed at the first place? See, if we can compress the blocks before writing into the main memory, then we can save a lot of bit flips, because the compressed area is exposed to relatively fewer memory cells as compared to the case where the block is fully written. So we have proposed a new compression algorithm that balances the trade-off between compression ratio and coverage to its best. So what is compression ratio and coverage, I will talk in the subsequent slides. And this compression algorithm is based on data similarity that exists in the word level. As you can see in this cache block, BAAA, these BAAA are different words, and the word A occurs with a very high frequency. And we have also confirmed from our experiments that these level of redundancy exists in the word level. And the idea is to remove the later occurrences of this word which occur with a high frequency. So in this example, word A is the most frequently occurring word. So instead of writing all the 3 instances, we will keep only the first instance and we will remove the later instances. So the compressed block will look like BA. However, in order to decompress the cache block, we need certain metadata. The first bit, called the compression bit, it tells whether the block has been compressed or not. The second field is called MFW index, that gives the first index of the MFW word, which is A in this case. So A occurs for the first time at the index position 1, so the MFW index is 0, 1. And the third field is MFW tag array, where we dedicate 1 bit for each word. And it tells if the bit is set to 1, that means we say that the block, that particular word was included in the compressed block. And if it is reset to 0, then that particular instance was removed. See, the later 2 instances were removed, that's why we are resetting the bit to 0. On top of compression, we further try to reduce bit flips by an encoding scheme where we change the bit patterns before writing into main memory. As you can see, this is the old data, and this is the new data. If we simply write the new data, it leads to a bit flip of 6, where the red ones are flipped bits. But because of compression, say suppose the block becomes 1, 1, 0, 0. Now the bit flips will be reduced, but it could be reduced further if we invert the data. So in this case, we are inverting. If more than half of the bits within that cache block are flipped, then it is better to write the inverted version and, rather than the original version. So this is indicated by a tag bit that indicates that this particular block, the bits of these particular words are flipped. And if it is reset to 0, that means the bits were written as it is. So after applying compression and encoding, the amount of bit flip reduces to 1, which was earlier 6. Now the block is compressed and encoded. So finally, as you can see, if we start writing from only one direction of the memory line, where the whole box is a memory line, then due to the frequent writing, the bits that are exposed to that compressed area, which is shown by the orange portion, and it leads to a more amount of bit flip. So instead of writing the compressed block from only one direction, we keep changing the orientation as well as the first position of writing the block. So after a W number of writes, the block has been shifted to a stride distance, and the orientation of writing is left to right orientation. And again, after some amount of writes, we start writing the block from the extreme right direction. And again, finally, after W number of writes, where S and O bits are both set to 1, we start writing the block from a stride distance and from the extreme right direction. So it will give a nice distribution of bit flips within the memory line, and the lifetime will be improved. So this particular work was published in, the first version was published in ACM IEEE ISL PDCA conference, and the extended version was published in IEEE Transaction on Computers. So this is the overall results where we have got a nice balance between compression ratio and coverage. So what is compression ratio? Compression ratio is the extent to which a block gets compressed. Say suppose the initial size of the block was 100. Now after compression it has become 20. So the compression ratio will be 20 upon 100 or 20%. So compression ratio should be as low as possible. On the other hand, coverage is the percentage of blocks compressible by a compression technique. So suppose out of 100 blocks, the algorithm was able to compress only 70 blocks. So the coverage will be 70. In most of the existing techniques, they either provide good compression ratio or coverage, but not both at the same time. But our technique provides a nice balance between compression ratio and coverage. That's why most of the blocks get compressed, and not only they get compressed, they compress to a very high extent. As a result, we can save a lot of bit flips, and on top of it, our wear leveling algorithm gives a nice distribution of bit flips, because of which lifetime improves over the existing techniques and performance also improved accordingly. Now the third technique. As I have already told, because of the non-volatility feature, the data which is stored in these memories can be easily stolen by performing a simple readout operation. So the sensitive data must be protected using encryption before writing to the main memory. But the thing is, if we encrypt the data block, it becomes highly random, and when these random data are written in the main memory lines, it introduces a lot of bit flips, which further complicates the issue of lifetime. So this particular work focuses on reducing the bit flips which are induced or initiated by encryption. So as you can see, if the original cache block is ACBB, and if we encrypt this cache line, the words using a AES-based counter mode encryption, the encrypted words become EA, EC, EB, and ED. These words are highly random in nature, and when we write these words in the main memory, it leads to a high amount of bit flips. On the right side, this is the pictorial view or the overview of our technique, where we see that a large number of words within the cache blocks are also repeated very frequently across different cache blocks. So in this particular figure, I have shown A and B are highly frequent words, which we call as popular words. So we try to store them in a table called popular word table, which is 64 entry table. And we skip the encryption of these popular words. So instead of encrypting A and B, which are popular, we simply keep a pointer to the index of this PWT. So A occurs at the index 4, so that's why we are keeping a pointer of 4 in its respective position. So when these partially encrypted blocks are written to main memory, a lot of bit flips can be are reduced, because we are not going to encrypt these words. So in order to manage this PWT, we need one more further table, which is called PWTT, or Popular Word Training Table, where we dedicate a small amount of time to train the PWT to collect the best possible popular words. The management of PWT and PWTT I am not going to explain in this presentation, and if you want to know it, kindly refer to our paper, which was published in IEEE transaction, IEEE TVLSI. So these are the overall results we get a significant improvement of bit flips and energy consumption, because energy consumption is an issue in PCM, and writes occupy the maximum energy consumption. So if we can reduce the bit flips, we can considerably reduce the dynamic energy consumption as well. It leads to a improvement of lifetime over two existing techniques, deuce and secret, and corresponding increase in performance. The final work, it is exploring avenues related to compression and encoding to reduce bit flips in encrypted memory. It consists of two works. The first work is compression and content-based selection procedure, or COSEP. I will explain COSEP first. As you can see here, in the left part, we try to compress the block using 3 individual techniques, out of which FPC and BDI are existing techniques, and COMP is the proposed technique. So as you can see, if the two smallest blocks are differ widely, if the sizes of the two smallest blocks differ widely, then we simply take the block which is smallest in size. And on the other hand, if the smallest blocks produced by the two techniques are of comparable size, then we go for bit flips. But in order to calculate bit flip, we might have to read the old content. And now we select the block that leads to a minimum bit flip. So in this case, BDI will be the clear winner, because it leads to a reduced bit flip, which is 70 compared to FPC, that leads to a bit flip of 100. The second technique is compression-assisted encoding. Here the block is compressed first, then the block is encrypted. And on top of this compressed and encrypted block, we apply encoding. But the benefit of encoding is this: since we are dedicating the tag bit to the compressed data portion only, so it results in a finer granularity encoding, and it leads to a significant improvement in the reduction in bit flips. Why fine granularity encoding works better than the static encoding, that I can explain you later, but for the sake of time, I will not explain in this presentation too much detail. So these are the different parameters. We have got significant improvement in bit flip and energy consumption. Lifetime will be improved accordingly. And we get a nice improvement of 16% and 15% for COSEP and CADEN, compared to a baseline where no compression and no encoding is applied. So non-volatile memories are widely considered as a potential alternative of DRAM in the main memory layer. They offer high density and low leakage power consumption, which are highly essential in order to build large capacity and energy efficient memory system. But on the other hand, downsides like low write endurance, high write energy, and latency thwart their adaptability. So for my thesis, I have proposed some architectural solutions that try to reduce the writes at the coarse and fine granularity. Also, I have proposed an intra-line wear leveling approach to uniformly distribute the writes within the memory lines. My thesis also works in the direction of providing security to the memory, where I encrypt the memory because non-volatile memories are susceptible to memory readout attacks. And for those encrypted memories, I also propose solution to reduce bit flips using partial encryption scheme and compression and encoding scheme. So our techniques lead to considerable reduction in writes and an eventual improvement in lifetime. So with this, I conclude my presentation. Thank you.
One round of applause for all the students, whoever are here, who have presented it. Now, I would like to request Mr. Hridesh Singhal, VLSI Conference Organizing Committee member, to come on to the dais to hand over the runner-up first Yeah, all the presentations were good. We do understand the hard work which has been put by every one of you. But we need to pick one runner-up and one winner as always. So I would like to call upon to the stage for the paper presentation of analog AI hardware and compute ecosystem for machine learning at the edge. Pratik Kumar onto the dais to receive the runner-up award from Hridesh. Sanjay, please, if you can also join us. The winner is for the paper Modeling of Anti-Board Attack in Bufferless NOC by Hardware Closen. I understand this team has left because they have a flight to catch up at 6 o'clock. So anyone from this team to come and pick the award on their behalf from their college? Thank you, Sanjay. Thank you, Hridesh. Thank you all.